Okay, so let's take a look at some of the properties of trig functions. Now, if you recall from previous lecture, we had a unit circle. That's how we motivated all 6 of the trig functions. Those were sine, cosine, tan, cotan, secant, and cosecant. And we did mention that for a unit circle, the first coordinate, the first component of the coordinate of a point corresponds to the measure of angle theta, central angle theta, and the second component, the y, namely, corresponds to the sine. So if you have x is cosine and y is sine theta. Now, if we want to determine the domain of sine and cosine, that means what does the real the measure of the angle could be? Well, the angle could start here at, let's say, 0, go to 90, 180, 270, 360, and you just continue forever, right? It can go in a counterclockwise direction forever. So the measure of angle itself could be all positive real numbers, or if I consider a clockwise rotation, which generates negative angle, same thing. Now I'm generating negative real numbers. Therefore, the domain of sine and cosine, we're going to say domain for sine and cosine are both all real numbers. That means negative infinity to infinity. The measure of the angle could be whatever. Now, what about, let's say the domain of tangent? Well, tangent, tan of theta, which is the ratio y to x, correct? Tangent, this is defined because x and y are all real numbers. So this is defined. The only place it's not defined is when we have division by 0, correct? So division by 0 is undefined. That means x cannot be 0, right? Well, 0, where does 0 occur? 0 occurs at 90 degrees, 0 occurs at 270 degrees, and every subsequent rotation, right, of those. And we can go, in fact, in both direction as well. We can go in a counterclockwise direction. There you go. This is negative 90. Now I'm at negative 270. And then every subsequent 180 degrees rotation in a clockwise rotation. So we can summarize this therefore as following. The domain of tangent is going to be all real numbers except minus pi over 2 plus every 180 degrees. Pi over 2 is right here, 90 degrees, right? That's pi over 2. 90 degrees. So with this notation, what I'm saying is that it's gonna be undefined for 90 and then every 180 degrees. You see that? Every 180 degrees. Whether we go in a clockwise direction or I can start at pi over 2, go I did counterclockwise before, I'm doing clockwise now. Clockwise direction now. There you go. So it doesn't matter. The key is that we start at pi over 2. Then we can go in either direction. That's what this says. Here in my notation, by the way, k is an integer. What are integers? Negative 3, negative 2, negative 1, 0, 1, 2, and so on. There you go. That's what k is. And the need for k here is just so we pick up all the subsequent rotations around the circle. All right. So there's the domain for tangent. Now, what about for cotangent? Well, cotangent of theta is the ratio of x to y. And remember, y is sine theta. So places where sine theta is 0, where y is 0, cotan is undefined. Okay, so domain of this one is going to begin all real numbers except where sine is 0. Where sine is 0. That means y is 0. Well, y is 0 at 0, y is 0 at 180 degrees, and again, every 180 degrees. And you can go in either direction again to get there, right? So I can start here and go 180 degrees, stop. Go 180 degrees, I'm going in a clockwise direction now. There. So we can pick up all of the zeros of y that way. Okay, and those are k pi. So you start at 0. When k is 0, you're at 0. And then you start every 180 degrees after that. You pick up another division by 0. And that is for cotangent. Now, what about secant and cosecant? Well, for secant of theta, secant is 1 over x, right? Which is 1 over cosine. Remember, x is cosine. So again, places where cosine is 0. First component is 0. Right there. Pi over 2 and every k pi. So this domain is going to be all real numbers except pi over 2 plus k pi. And I'm getting every information so far. I'm getting it all from the unit circle, by the way, folks. So that's why I'm not a proponent of memorization. So I hope that you actually do it like I do it, so you don't have to memorize. It's really a nightmare to memorize these, right? And that's not the right way of doing it anyhow. Okay. And secant, now for cosecant, again, places where you have division by 0 means y is 0. So look, I'm looking at the unit circle, y 0. Here's 0, there's 0. So it happens every k pi. Domain is places where y is 0. And remember, y is sine theta. So we're looking at places where sine is 0. Sine is 0 every 180 degrees starting at 0. And there we have the domains. Now, for the ranges, I can see for the ranges here also for x and y. Look at, for example, the x. Your x maximum is 1, minimum -1. You have everything in between, right? Look at the domain. I mean, that was domain. Look at the range, the y values. The y values, the same thing. They're bounded between -1 and 1. So both sine and cosine are, we say, they're range bound. That means they're bounded between -1 and 1. So for sine theta and cosine theta, the range now is going to be between -1 and 1, both of those, because they're within the confines of the unit circle, right? Another way we can write it is this sine theta and separately cosine theta. Remember, y values are the value of the function, lie between -1 and 1. Or we can write it as the following. We can say absolute value of sine is less than or equal 1, and absolute value of cosine is less than or equal 1. These mean the same thing. All right. Now, let's do it for, let's say, secant. We're doing ranges now. Okay, we're doing the range of trig function is what we're doing. And, oops, sorry. Let's do for secant. Secant theta. Well, absolute value of secant is 1 over absolute value of x, right? Which is 1 over absolute value of cosine theta. Okay. Now, this is going to be greater than or equal to 1. Why? Since absolute value of cosine theta is less than or equal to 1. We just got that from earlier, right? Therefore, we just showed that absolute value of secant theta is greater than or equal to 1. That the output of the function secant function is secant theta. So this means the y values are greater than or equal to 1. So this is equivalent to secant theta less than or equal -1, or secant theta greater than or equal to 1. Now, where does this come from? It goes back to our work in algebra. First, let me just put that because this is the range of secant. Okay, and I'm going to write it now. Range of secant less than or equal -1 means from -1 to -infinity to -1. Union greater or equal 1 means 1 to infinity. So this is the range of secant. Okay, now the reason to justify what I have here, absolute value greater than 1, means this. Goes back to algebra days. Absolute value of x greater or equal 1 means the following on the number line. Let's say I have a number line. This is a number line. Here's 1, here's -1. Greater than or equal 1, so that means everything above 1, right? That's going to be greater than or equal 1. Now, everything that's less than or equal -1 in absolute will also be greater than 1, wouldn't it? So, for example, -2. Absolute value of -2 is 2. Isn't that greater than or equal 1? It is greater, but not equal, but that's good enough. So that's why anytime we have absolute value of x in general greater than or equal k, where k is positive, then we can rewrite this as x greater than k or x less than -k. And that's exactly what I've done here. The k is 1 in the case of secant theta greater than or equal 1. My k is 1. So that's what I used. All right, so it goes back to algebra days. So there is the range of secant. Now, likewise, we can do the range of cosecant, right? I can say, okay, let's do cosecant theta now. The range for it. I can say the absolute value of cosecant theta is greater than or equal to 1. Okay. And that's again because cosecant is 1 over sine, right? And that is because I have 1 over sine theta, and absolute value of that is going to be greater than or equal to 1. All right. And the reason again, because this is true since absolute value of sine is less than or equal 1. Think of it this way. For example, I know 1/2 is less than or equal 1. The reciprocal of that, which is what cosecant is, the reciprocal of 1/2 would be 2. Wouldn't 2 be greater than or equal 1? So that's the kind of work we're talking about. If 1/5 is less than 1, then reciprocal of that, 5, would be greater than 1. And that's exactly what we're saying in here. Because absolute value of sine is less than 1, its reciprocal is going to be greater than or equal 1. All right. And then, so we just established this one. Absolute value of cosecant is greater than 1. That means now, using algebra, when we say absolute value of cosecant theta is greater than or equal to 1, this means cosecant of theta is less than -1, or cosecant without the absolute value has to be greater than or equal to 1. All right, and the interval notation for this is just like for secant, -infinity to -1, union 1 to infinity. That's for this portion of it. The other one is this portion. Okay, and we have the ranges for them. Now let's look at for tangent. For tangent and cotangent, it's a little tricky, not really bad, but to show the range of these, well, tan theta, let me just say that's the range for cosecant. And we're doing now tangent. Okay, so for tangent, here's what I can do. We know that tan theta is the ratio of y to x, right? So whatever that is, call it a. Now, on a unit circle, we know x squared y squared is 1, correct? So From this, we get y is equal to ax, correct? From definition of tangent. So I'm going to replace y with ax quantity squared in my equation of a circle. Then I can factor the x squared. I get 1 plus a squared is 1, correct? And I can solve for x squared. X squared is 1 over 1 plus a squared. And then take the square root of both sides. I get 1, x is equal to plus or minus 1 over square root of 1 plus a squared, right? Now you can plug this in back in here and solve for y. Okay. And when you do, I'm just going to give you the answer. When you do plug it back into the equation of a circle, we get y to be plus or minus a over square root of 1 plus a squared. Okay, now you can see that for any a, any real number a, the denominator will never be 0 in both cases for x and y. There will never be 0, so there will always be an output for x and y. True, regardless of what a is. So I'm just going to write that for any a and real number a, we can say that x and y exist. Well, if they exist, then that means the ranges are real numbers, right? Because y exists, x exists, therefore a exists for all real numbers. So that means the range for tangent is all real numbers, negative infinity to infinity. Now for cotangent theta, we can kind of do a similar work. Cotangent theta is the ratio of x to y. Call that a now, or b, doesn't matter. Let me do b so it's not the same as tangent. From this, x is equal to by. The equation of a circle, x squared y squared is 1. So x squared is going to be b squared y squared plus y squared is 1. Factor the y squared and divide by the binomial. Take the square root, we get plus minus 1 over. Notice it's almost like tangent, right? Just like this one. So that's what your y is now. And plug it back in for y in here, solve for x. I did. And there, let me just give you the answer. I got a, or actually, sorry, b. I'm doing b now, just to be different from tangent. So I get b over square root of 1 plus b squared. And same methodology with tangent. The denominator is never 0 because you're squaring it. You're squaring the b. So that means x and y will exist for all real numbers, and x, y individually are not 0. Therefore, put these together, therefore we can say that the range of cotangent is going to be from negative infinity to infinity also, just like it was for the tangent. All right. So we have the domain and ranges of these trig functions. Now, the next thing I want to talk about is that if you have a point on a circle, this is a separate idea now. Suppose I have a point on a circle, this point P on the circle. Could be unit circle, could not be, doesn't matter for what we're talking about here. So here's the point on my circle, part of my circle, there. Okay, so this is a point again corresponding to angle theta, right? Now it turns out that and this point is identical to all the points that are also in the form theta plus 2 k pi, right? Remember, k is integer here. K integer. So what I'm saying here is this. Suppose I have a point here. If I go around the circle once, I end up exactly with the same spot. So that's 2 pi. If I go one more time around the circle, now I've gone 4 pi. Another rotation, another 2 pi, and another 2 pi, and so on. In a negative clockwise direction, I start at point P and go another rotation, negative 2 pi, negative 4 pi, negative 6 pi, and so on, right? All of these are the same point, aren't they? I always end up at the same point. Okay, so if I end up at the same point, that means the trig functions, the value of trig functions are all the same, aren't they? So that's what I want to generalize now. The trig, let me just say it this way. The values of trig functions of theta are the same as, or I should say, because we're using theta plus 2k pi, our base is theta. So the value of trig function of theta plus 2k pi are exactly the same as the values of the trig functions of theta. Okay, which tells us, and remember, all of these subsequent rotation give us angle that are coterminal, that have the same terminal side, right, as angle theta. True. So if I start, let's say, at point P, and I go one rotation around and I end up at P, well, they have the same terminal side. And that's what that circle does. Okay. So it's for that reason that we say, for this very reason that we say the trig functions are periodic. That means at some point later, some later point, they repeat themselves. Okay, so what is the definition of a periodic function is this. If the value of the function at theta plus some point at some point later is equal to the value of the trig function of theta, then we say f is periodic. So all six trig functions are periodic, means they repeat themselves. The value of trig functions, they just repeat themselves beyond a certain point. Okay, now the smallest of the p's that are in here, if they exist, the smallest p, the smallest value of p here, and p, by the way, is a positive number here. The smallest p for which the function becomes periodic, for which the function is periodic, is called the fundamental period of the function of f. Okay, and there you have it. So for trig functions, well, for some of the trig functions, the period would be 2k pi. Okay. And for others, the period would be k pi, for example. There. And that's what the role p plays. And here, the period is positive. Remember, period is positive here. All right. So let's take a look at, for example, for sine. If you look at sine of theta plus 2 pi will give you exactly sine theta. That's one rotation in a counterclockwise direction. So sine, cosine, all of them would be periodic. The period of sine and cosine is 2 pi. So that means cosine of theta plus 2 pi will give you exactly cosine theta. Secant is also periodic, plus 2 pi gives you secant theta. So in other words, what we're saying here is that the period of sine, cosine, secant, cosecant are 2 pi. There you go. Keep that in mind. For those 4 trig functions, the period is 2 pi. Okay. In the basic form. That's if you don't compress them, stretch, and do funny things with them. Now for tangent of theta plus pi, not 2 pi, gives you tan theta. That means the period of tangent, and so is cotangent, are both each pi. There, this period is pi. So for the 4 trig functions, sine, cosine, secant, cosecant is 2 pi, and for tan and cotan is just pi. Okay. Now, we are usually interested, by the way, in trig values over one cycle or one period because they repeat themselves beyond that. So if I look at just one period, okay, if I look at just one period, so here's my unit circle. Okay, and here's x, there's y. And remember, our point here, P, corresponds to cosine theta, sine theta. First component, x, is cosine theta. Second component, y, is sine theta. So if I label my coordinate system, actually this is going to help me now. Negative cosine, negative sine theta. This is just my way of labeling the coordinate system. It helps me with the following. All 6 trig functions in the first quadrant are positive because cosine is positive, sine is positive, right? So all are positive. All 6 trig functions are positive of angle theta, are positive. In the second quadrant, notice sine is positive, right? Sine is positive, but cosine is negative. Therefore, trig functions involving sine and cosine, we can determine which is positive, which is negative. So in Q2, in second quadrant, sine positive, cosine negative, right? Therefore, tangent, which is ratio of y to x. Remember, this is, let me do this. X is negative, y positive. Here, x negative, y negative. X positive, y negative. And might as well do it this way. X positive, y positive. So we can get the sign on all 6 trig functions in any quadrant now. In Q2, tangent of theta is going to be negative because x is negative, y positive, and tangent ratio y to x. Cosecant, which is the reciprocal of sine, is going to be positive because sine is positive. Secant, which is reciprocal of cosine, is going to be negative because cosine is negative. You see that? Cotangent, reciprocal of tangent, will be negative because tan is negative. And so on and so forth. Okay, and likewise, you can do this for third and fourth quadrant. Okay. Now, let's move on to our fundamental identities now. These fundamental identities, I already mentioned some of them just a few minutes ago, like cotan reciprocal of tan, secant reciprocal of cosine, and so on. Fundamental identities, let's talk about them. First, cosecant. Cosecant is 1 over y, so that's going to be 1 over sine. This is also known as the reciprocal identity. So is the next one. Secant is 1 over cosine. Another reciprocal. Cotangent, reciprocal of tangent. So these 3 are often referred to as reciprocal identities. Let me write that. These are reciprocal. Remember, reciprocal means 1 over. That's what these are, 1 over. Next, we go on and talk about ratio identities. So these are now my ratio identities. With ratios are just that you form a ratio. So tangent theta is the ratio, means quotient of sine over cosine theta. Cotangent theta as a ratio identity, that's the ratio of cosine to sine theta. All right. And then we have our famous Pythagorean identity, which is named after Pythagorean. Okay. X squared plus y squared is equal to 1. And here x, again, remember x is the x component is cosine of theta squared, and y is sine squared equal 1. Something about the square, by the way. When we say cosine squared, we should really write them like that, right? But very common to write it like this. They put the square between s and theta. For trig functions, it's very common to do it. Now, one thing I want to note right away for everyone, because I've seen this so many times. Sine theta plus cosine theta does not equal 1. Okay, that's not Pythagorean identity. It has to be squared. Okay, so this is incorrect. Please make a note of that somehow. All right. Now, from the Pythagorean identity, we actually get a couple of very useful identities. Now, check this out. We know that cosine squared plus sine squared is 1, right? So if I divide everything by sine squared, for instance, sine squared, sine squared. Well, cosine squared by sine squared, that's cotangent, right? Sine squared by itself is 1, and 1 over sine squared is cosecant squared. So there you go. We get a new identity as a byproduct of Pythagorean identity. So if I need an identity that connects cosecant and cotangent, this is my identity. Let's take a look at cosecant squared plus sine squared equal 1. Now this time, instead of dividing by sine, let's divide by cosine. So I'm dividing both sides, everything by cosine squared. Now cosine, cosine, that's 1, the ratio. Sine to cosine, that's definition of tangent, right? That's the ratio identity for tan. The reciprocal identity for 1 over cosine is secant. And there you go. Isn't that cool? Now, I have actually a new identity that relates secant and tangent together. And again, I want to emphasize, if you want to memorize something, memorize Pythagorean, because it's so easy to memorize. But I would not memorize these other two. You can create them, like what I call on demand. If you need them, divide either by sine or cosine, and you see what do you get. All right, and now let's end this with the even-odd identities, right? Even-odd properties. The even-odd properties give us the even-odd identities, which is really for negative angle. So let's call these negative angle identities. Negative angle identities. These all involve negative angles, and they all have to do with whether the function, the trig function, is odd or even. Now, the odd functions. Sine is an odd function. Sine of negative theta equals negative sine of theta. Okay, I'll show you why in just a moment. Tan of negative theta, tan is also odd. It's negative tan theta. Cotan, odd, negative cotan theta. And we know what the implication is on the graph, right? The odd and evenness of functions. Remember, a function is odd means its graph is symmetric with respect to the origin. And in all cases here, f of negative x equals negative f of x, which is the condition for oddness. That means all four graphs, all four of these are going to be symmetric with respect to the origin. Now the even functions, the even trig functions, there's only a couple of them. Cosine of negative theta is negative, actually it's just cosine theta of a positive angle. Okay, and secant, which is the ratio of 1 over cosine, therefore is going to be even also. So in this case, here's where f of negative x is equal f of x for even function. Again, the implication for the graph is that the graph is symmetric with respect to the y-axis. Now to kind of show you how this works for, let's say, one of them, suppose I have, here's my unit circle, okay, and here's the point xy, right? The x component, remember, is cosine, the y component sine. Here's the angle, positive angle theta, and this would be the negative angle theta, right? There you go, negative angle theta. The coordinates of this point, because it's in the fourth quadrant and by symmetry, is also x, but this y is negative y, correct? And again, if I think about the first component as cosine, second component as sine, so you can see that whether angle theta is positive or negative, it has the same x. But then we said x is cosine, y is sine. So you can see that cosine of a negative angle is the same as cosine of a positive angle. And similarly, you can do this for the odd ones. Okay. Alrighty. Now, let's take a look at some examples for the things we just talked about in this section. Let's say I want to find cosine of 33 pi over 4. Now for this one, remember, this is when we said the trig measures of, let me go back here, right up here, there you go. The values of trig function of theta plus 2k pi are the same as measure of angles theta. So what I need to do in order to find cosine of 33 pi over 4 is to find the terminal side of this angle. Okay, so now 33 pi over 4, well, 33 pi over 4 is 45 degrees, right? So if you do 33 times 45 degrees, what are we going to get? Let me multiply that real quick, times 33. That's 1,485 degrees. If you divide that by 360, you get 4.125, right? 4.125. So that means 4 revolutions and then some. Now 4 complete revolutions, 4 revolutions is 1,440 degrees. So if I subtract 1440 from 1485, I get 45 degrees. So this thing is going to, the angle, here's my unit circle, right? The angle is going to go 4 complete rotations. 1, 2, 3, 4 complete revolutions. And then it's going to end up at 45 degrees. There you go. So it will be coterminal with a 45-degree angle. So that means this is equal to a simply cosine of pi over 4. Isn't that cool? Now we can go back to our unit circle and say, okay, well, cosine of 45 degrees, that's going to be equal to root 2 over 2. Because that was one of the special angles that we talked about. And that's it. There's the answer to that one. Next example, let's say for this one now, we're going to do this different. Suppose I'm given that sine of an angle is 4/5. Okay, and the cosine of the angle is Let's make it negative 3/5. We want to find the remaining trig functions. Okay, of angle theta. And note here, I don't even know what the angle theta is, but I know the x and the y, right? X is negative 3/5, y is 4/5. So I can actually locate this point, correct? And x is negative 3, y is 4. Let me actually do a better drawing here. So here's, let's say, negative 3, that's 4. This is a point negative 3, 4, isn't it? X is negative, y positive. So the point must be in the second quadrant. Therefore, I can determine the radius of the circle. The radius is going to be, let's see, actually these are fifths, right? That's fine. 3/5, 4/5. So I can determine the radius to be x squared plus y squared, square root of. And that's going to be a unit circle. Okay, that's fine. Negative 3/5, and this is 4/5. So this is going to be a unit circle, and the reason, because I get 9/25 plus 16/25. So that's going to be 25/25, and that's 1. Okay, so these are points on a unit circle, but it's not a special angle. Okay, it is not a special angle. It's not a 30, 40, 45, 60. And there we have it. Now, because these are points on a unit circle, therefore now I can do tangent would be y over x, or you can use ratio identities. At this point, you have a lot of tools at your disposal that you can do. So if I go the ratio y to x, I can go 4/5 over negative 3/5. So that's just going to be negative 4/3. Cotangent will be reciprocal of that, using reciprocal identity. Okay, we know cosine, so we can do secant. Secant theta is 1 over cosine theta, right? Which is 1 over x. That's going to be 1 over negative 3/5 or negative 5/3. And what about cosecant? Cosecant is 1 over y, and that's going to be 1 over 4/5 positive or 5/4. And there we have all the trig measures of that angle. All right, now let's take a look at a couple of more examples and we'll be done. Okay, so for this next example, suppose tangent of theta is now 3/4, and let's say sine is negative. So we have a condition here on the angle. We want to find the exact value of the remaining trig functions. All right, so here's what I can do. The fact that tangent is positive in the first quadrant and the third quadrant, because in both quadrants ratio y to x is positive. Okay, and because sine is negative, remember the way I recall my axes, the vertical axis is sine and the horizontal axis is cosine. Okay, so this is kind of for me to remember the sign on these trig functions. Therefore, if sine is negative, that means I have to be below the x-axis. So that puts the angle either in third or fourth quadrant. Agreed? So based on sine negative, I'm going to go sine theta is less than 0 here, and sine theta is less than 0 here. Now, tangent is positive. Tangent is positive in the third quadrant, but in fourth quadrant, tangent is negative. And the reason is because x is, remember, tan is ratio of y to x. y is negative, x is positive, so that ratio is negative. That's how we know tan is negative. All right, therefore the angle must be in the third quadrant. True. So in the third quadrant, now I'm going to draw my angle in the third quadrant, and the ratio is y is 3, x is 4. There you go. That's the measure of the angle theta. And in the second quadrant, both x and y are negative. So this is going to be negative 3, and this is negative 4. That's y, and this is x. Because tangent is ratio of y to x. That's why this side has to be negative 3. Now, the radius, using Pythagorean, the radius is going to be negative 3 squared plus negative 4 squared, square root of. And that's going to be square root of 25 or 5. So this is not a unit circle. It is not a unit circle. This is a circle of radius 5. But whatever it is, now we can just kind of quickly get these answers. Cotan, reciprocal of tangent, it's going to be 4/3. Done with that. Sine is the ratio of, because this is not a unit circle, sine is going to be y over r, correct? So it's going to be negative 3/5. Reciprocal of sine is cosecant, is 1 over sine. Right away I can say that's negative 5/3. Cosine of theta is going to be x over r, so it's going to be negative 4/5. Therefore secant, which is reciprocal of cosine, right away I know that's going to be negative 5/4. And there we have those measures done right away. Okay. And let's finish this off with just some negative angle identities here. These will go quickly. Cosine of negative 30 degrees. Well, cosine again is an even function. Therefore, cosine of negative 30 and cosine of 30 will be the same. Cosine of 30 degrees is root 3 over 2. What about sine? Sine of, let's say, negative 3 pi over 2. Well, that's the same as negative sine of 3 pi over 2, because sine is odd. And sine of 3 pi over 2, remember that's the quadrantal angle. 3 pi over 2 is this angle. And the coordinates are 0, negative 1. Sine is going to be negative 1, so that's 1. See, that unit circle stays with me for a long time. And what about if I have, let's say, tangent of negative pi? Well, tangent of negative pi is negative tangent of pi. And tangent of pi this time on my unit circle, negative 1, 0. Here's pi, right? Theta is pi. Tangent ratio y to x. It's going to be negative 0 over negative 1 or 0. Right? And just to do one more, let's say I want to do a cosecant of negative pi over 3. Again, cosecant of negative theta is negative cosecant of theta. And cosecant of pi over 3, remember that's 1 over, cosecant is 1 over sine of pi over 3. And sine of pi over 3 is root 3 over 2. Okay, so therefore this is going to be negative of invert and multiply 2 over root 3, which I can rationalize and get negative 2 root 3 over 3. And there we have it. So negative angle identities, we usually use the odd even properties to do that. And that's, by the way, also is important later on in a future section. Let's say we want to graph negative pi x. We want to graph that sine function. So what I'm going to do is I'm going to write that graph of sine negative pi x is going to be negative sine pi x. So I'm going to graph this function, and then the negative, I'm going to reflect it about the x-axis. So the negative angle identities come in very handy, especially when we graph functions. All right, looks like we are done with this lecture. Hopefully you will able to find or follow everything we've done. We covered a lot of ground. So we're done with the section on properties of trig functions. Thank you for watching, everyone.